Today we want to open up with this problem because it's got some cool stuff in it. We're given the sine of alpha and the cosine of beta. We're given information about alpha and beta, and we're asked to find the exact value of tangent of alpha plus beta. It's that exact value thing. It's that find the exact value thing that takes all the simplicity out of the problem, right? It's like, I'll find the exact value. And so we're like, oh, exact value. Because if we didn't have to find the exact value, I could just grab sine alpha is -8/17, use my calculator to find the reference angle and figure out what alpha is. Put that reference angle in quadrant 3, and then figure out what beta is, add the two together, and hit the tangent button. Let's do the problem as intended. We're told that sine of alpha is -8/17. And that alpha is in quadrant 3. Okay, that makes sense. Sine is negative. That means we're in quadrant 3 or 4. And so we're being told that it's quadrant 3. We had a choice of 2. They got to tell us which one it is. And then cosine of beta is -1/4. So beta is in quadrant 2. And we want the exact value of tangent of alpha plus beta. So tangent of alpha plus beta is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent beta. So this is the sum identity for tangent. And now, right now, you're all looking at me like, oh, Leach, you did not tell us this one. It's like, oh, no, I expected you to read about it. And you're like, oh, that's not cool, man. Read a math book, uncool. I'm like, oh, I know, right? Dick move on my part, I guess. But that's okay, we're there now. The point is, I've only got sine of alpha, and I need tangent of alpha. I've got cosine of beta, but I need tangent of beta. So we know that sine and cosine are related, but sine and tangent has that cosine in between. If I want to use sine divided by cosine equals tangent, I'll need to know the cosine of alpha. So what we're going to do is we're going to take this information, we're going to draw a triangle that fits this description, not with the negative part, although we can. We're going to have alpha in quadrant 3, but we're going to worry about the 8/17. We're going to treat 8 as opposite and 17 as hypotenuse. So when we look at this -8/17, we can set up 8 as opposite and 17 as hypotenuse. And then from there, since we have opposite and hypotenuse, we can go figure out the adjacent side, and then we'll have opposite over adjacent to get the tangent. We'll try to draw this in quadrant 3 where it's supposed to be. So here's our x-axis. Alpha is in quadrant 3. The side opposite is 8. And the side adjacent is 17. Oh, sorry, the hypotenuse is 17. So this is a picture of where alpha is. Opposite is 8. Hypotenuse is 17. It's in quadrant 3, so opposite is like a -8. So to figure out the adjacent side, I'll go 8 squared plus adjacent squared is 17 squared. So the adjacent side is the square root of 17 squared minus 8 squared. Let me get my calculator out. I don't want to use my phone calculator. So the adjacent works out to a nice 15. So we've got an 8, 15, 17. Triple. Could have saved ourselves some calculation if we ignored that. The important part is from this, we can get the tangent of alpha is opposite over over adjacent. So 8 over 15. We do have to worry about negatives and positives, but we're in quadrant 3. Tangent is supposed to be positive. And if we're in quadrant 3, this 8 opposite was going to be negative, but then our adjacent would also be the negative. So we're good. Tangent of alpha is 8 over 15. So we're going to be able to get tangent of alpha plus beta without knowing alpha and without knowing beta. Tangent of alpha is 8 over 15. Then we need tangent of beta next, and we're going to do the same thing. So beta is -1/4, and beta is in quadrant 2. So I'm going to draw an angle with an adjacent side of 1 and a hypotenuse of 4. And I'm going to put this in the second quadrant. So an adjacent side of -1 and a hypotenuse of 4. And I don't have a good place to put beta. Before I start writing this down, Michael, I'll do beta first because it's in quadrant 2. And Michael, nah, it's fine. It'll be fine. It wasn't fine. So I'm going to take the adjacent side, and I need to figure out the opposite side for beta. I need to figure out the side opposite beta. So I'm going to do opposite squared plus adjacent squared is hypotenuse squared. So the opposite will be the square roots of 16 minus 1. So the square root of 15. So from here, I can calculate tangent of beta as opposite over adjacent. And I'm going to use the negative because tangent is negative in quadrant 2. Yes. So I want the positive because tangent is positive in quadrant 3. So if we think in terms of x and y being positive and negative, for alpha, the y is negative, but our adjacent is also a -15. So when I say opposite over adjacent, I do -8 divided by -15. It becomes +15. We can also think of it in terms of just reference angle. Opposite 8, adjacent 15. It's positive because we're in quadrant 3. So we can go to the end, or we can get the individual signs of our opposite and adjacent. So tangent of beta is negative √15 over 1. Any questions? This is not going to be acceptable to a computer because this is not simplified. This is not simplified because I got a fraction, and in the numerator is a fraction, and in the denominator is a fraction. This is unacceptable. But from here on out, we're just going to be doing algebra. Okay. Ready for some algebra? Of course, we're always ready for algebra. Because that's just fun. Complex fractions? Heck yes. Yes. The other one's a negative, right? Because it's tangent alpha plus beta. All right. So good news is there are multiple ways for dealing with complex fractions such as this one. Bad news is there are multiple ways that we can deal with complex fractions such as this one. I don't know which one you're going to like. So let's do a couple. Let's take this as a starting point. And we have to simplify this complex fraction. The reason that I want to label this as simplifying a complex fraction is that in the age of the internet, half of the battle of dealing with your math class outside of your math class is knowing what the shit is called so that you can search for it on YouTube. So if you want to ask Professor YouTube what the F is going on here, you want to ask about simplifying complex fractions. There's also this square root of 15 in there. That's just another number. Just don't worry about that part. That's not the messy part. The messy part is I got some fractions inside my fractions. These are not two great places to put things straight together. So my favorite trick for dealing with complex fractions is to multiply by 1. The reason I'm going to do one big 1, because the denominator up here, the thing that makes a fraction up here is a 15. Ugh. Down here, it's the same thing. So because my denominator in the numerator, that's just awful. English is a terrible language for communicating. The denominator of my numerator is a 15, and the denominator of my denominator is also a 15. That means we can get away with multiplying by one big 1. I'm going to multiply the top and bottom by 15. That's how we deal with complex fractions. So I'm going to multiply we're going to multiply on the top and the bottom by 15 because the thing that makes this a complex fraction is the denominators in the numerator and there's a denominator in the denominator, all these extra denominators running around. But if we multiply by the common denominator of all the denominators that are messing things up, that clears them out. But we only get to multiply by 1. So I'm going to take my 8 over 15 plus a minus is going to be a minus. And there's a square root of 15 over 1. And in the denominator, I've got a 1 minus multiplied by a minus is a plus. And I'm going to 8 square root of 15 over 15. So first, I'm looking at all this. I'm saying these 15 denominators. Well, there's not 15 of them. Those 2 15 denominators. English once again. Failing me. If I multiply on top by 15, I cancel out that denominator. If I multiply on the bottom by 15, I cancel out this denominator. So that's what we're going to do. We're going to multiply the top by 15. And we're going to multiply the bottom by 15. Here we are multiplying by 1. We got to distribute it properly because I've got to multiply the entire numerator by 15. 15 multiplied by this 8 over 15. I'm going to write out all the details because everybody likes to see all the details. So we're using the distributive property here. Because the distributive property is multiplication distributing over addition. And I get this 1 over 1 times 15. So first we multiply by 1. Now we're doing the distributive property. Now the thing that we planned to happen happens. The reason we did this is to make this happen. This is what we wanted to happen. This is what we identified as the problem. Complex fraction because we have a denominator inside of our numerator. So let's multiply to get rid of that denominator. Now what we have over here is 8 over 15 times the 15. The 15's cancel, we're just left with 8. But over here, I still have the 15. In the denominator, I've got this 1 times 15, that's all 15. And in this term, the 15's cancel, so I'm left with 8 square roots of 15. No longer a complex fraction. It's no longer a fraction inside of our fraction. At this point, we might draw the line here and say this is acceptable. If you were typing this out and you typed this at me, I'd be like, oh, that's cool. I'm okay with this not being simplified. But is the computer going to be okay with this not being simplified? Actually, I didn't even check. Oh, okay. Awesome. Canvas, consider me impressed. Is that the right number? Yeah. Because I did not want to rationalize that denominator. Any questions? This is a weird place to draw the line to say you got to simplify it and leave a radical, leave it unrationalized. That's where I personally would draw the line. But it is kind of a strange place. Traditionally, you don't want radicals in your denominator. But I guess if you're working with computers and calculating machines, then I don't even know why you want the exact answer anyway. Then you find out this was an algebra exercise. This was never about the trigonometry. Any questions? So many times your next math class is all your math class is all about the previous class. Well, hey, remember the previous class? And you're like, oh no. It's like, well, you will now. How would you rationalize this? What if I said you can't have a square root in the denominator because rules? You know how to rationalize? Not quite. We would multiply by 1, but square root of 15 wouldn't be sufficient because square root of 15 times the square root of 15 would be a 15, but then I'd be multiplying the square root of 15 by this 15 over here. And I would just shift the burden of the square root of 15 from this term to the other term. To fix this, we would have to multiply by the conjugate of the denominator. Yeah. If you want to rationalize the denominator, you would multiply by the conjugate of the denominator. Technically, you'd be multiplying by 1, but the form of the 1 needs to be the conjugate of the denominator. It just means change the sign in the middle. So you would take 8 minus 15 root 15 over 15 plus 8 root 15. You can actually rationalize the numerator, but no one ever asks you to do that. But because there's 2 terms down here, you would have to multiply by not just the square root of 15, but the conjugate, which just means change the sign in the middle. And we're going to be using our difference of squares. Now we have to multiply by 1, so I have to do this on top and bottom. This will remove the square root from the denominator. Because when we multiply, the O and the I will cancel out. So I'd have 15 times 15 is 15 squared minus 120 root 15. Is it 100? How much? $120. 15 squared is 220. Yeah, 225. So then, but then we have a plus 8 root 15. This is a plus. This minus AB and then the plus AB canceling out is why this works. And then we multiply 8 times 8. We have a minus 64. The square root of 15 squared is just 15. So because the O and the I cancel out in our FOIL, that's how we get rid of the denominators. These 2 terms cancel out. This was the point of doing this multiplication. We wanted to get rid of the square roots in the denominator, so this is how we get it. In the numerator, we have to multiply the same way. We're going to have radicals in our numerator, but that's going to be okay. Radicals are okay in the numerator, not okay in the denominator. I have 8 times 15 is 120. Minus 64 root 15. Minus 15. 225 root 15. Plus 120 times 15. And right now, Canvas is like, oh man, why are you rationalizing? You didn't have to rationalize it for this problem. I go, I don't know, man. You're the one that puts an 8, 15, 17 triangle in and then makes the other one a 1 root 15, 4 triangle. How's that right there? You're the one that wants to procedurally generate problems You tell the machine to not put radicals in there. I still haven't sorted this out. You can probably guess that I'm not going to because I'm out of space. I'm the only person that gets to do this, by the way. Everybody else has to like have a number, take a box for it. I'm the only one that can be like, wave my hand, no problem. Look at all the algebra that happened in this problem. This is where we did trigonometry, right? Where we wrote tangent of alpha plus beta, and then we wrote the sum identity for a tangent. And then it was like, oh, knowing opposite adjacent hypotenuse. And then it's like, oh, algebra. But these are the things that you want to search for, incidentally. If you're looking stuff up on the YouTube to reinforce algebra skills. What we were doing here was simplifying a complex fraction. The other things that we were doing were rationalizing the denominator. And we multiplied by the conjugate. This was to get rid of the radical. That's what rationalizing is, getting rid of the radical. Leaving denominators leaving denominators with radicals in them. That's confidence. That's like anti-authority. Because you get rid of radicals by squaring them. You don't want radicals, you want squares. And you definitely don't want radicals undermining you in the denominator. Maybe that's why I don't radicalize my denominator. Are you trying to tell me what to do? And the math teacher was like, well, it's literally my job to tell you what to do. Well, you can't tell me what to do. You're going to flunk math, Leach. So the exact value thing is why we wanted to use, we had to use trig identities. The exact value part is why we needed trig identities and not inverse trig functions. So when we were told that sine of alpha is -8/17, and that alpha is in quadrant 3, thank you. We could use inverse trig function to find a reference angle. So the reference angle for alpha is a sine inverse. Don't worry about the negative parts of 8/17. So mode, we're in degrees. Sine inverse of 8/17. So I'm going to take a 28.07 degree angle and put it in quadrant 3. So I'm going to have to add a whole 180 to it. So our reference angle is 28.07 degrees. In quadrant 3, then if cosine of beta is -1/4 and beta is in quadrant 2, then we can find the beta reference angle by doing a cosine inverse of 1/4 and putting that in quadrant 2. So cosine inverse of 1/4, 75.5 degrees. And then putting that in quadrant 2. Now that we have alpha and beta, we could just add those two together. And find the tangent of this. I should have pushed tangent first. But we're not getting the exact value. The exact value, since we have a calculator, that's one of the reasons we don't really need to rationalize this, but I have 8 minus 15 times the square root of 15. Divided by 15 plus 8 times the square root of 15. They're not exactly the same because for alpha and beta, I rounded my angles off to the nearest 100. And I didn't use all of those digits, but it matches up all the way out to the 0.83. 100,000, 10,000, 100,000, million, 10 million. To the nearest 10 million, we're good. Any questions? How's everybody okay? Yes. I think that's just a quirk of the way the problems were assigned. I hadn't even noticed. Yeah, alpha in quadrant 3. Different time. I do not know. I think it's just a quirk of the way the problems were written. There's not some alpha is always quadrant 3 conspiracy running around. At least that's what I need you to believe. Any questions? Comments? Stop your mind. All right. Let's take a break and then we'll come back and talk about some more